All right, welcome back, everyone. Like I said in an email, we are going to do a virtual lab today. This is lab number 6. We're going to be looking at flexural properties of laminated versus solid floor joists. And there's an introduction that I'll let you read on your own time, and floor noises and things like that. What we're primarily looking at are these flexural properties, and we talked about bending stresses before with the moment and sizing beams and deflection and all that kind of stuff, right? Well, this lab hopefully will hit on a lot of these aspects. So what we're going to be comparing really are solid. It's a solid 2x12 and a TGI. That's one of our wood I-joists. Like I said, you can read more about that in the beginning. What we're going to be measuring during the lab portion is the load and deflection. So if there's a certain amount of load on this beam, how much deflection will there be? And then we're going to divide it out, take load divided by deflection for that last little value. We're going to do that for 2 different samples for the solid 2x12 dimensional lumber, 2 different TJI members. And then we'll just do 1 LVL glue lam just for fun, just to see. It's so much stronger. It's not really used in the same context. We aren't actually comparing them. When it comes to the calculations, at the end of the video, I'll go through some of this with you, but it should be somewhat familiar. We talked about this stress before, but at the end of the video, like I said, I'll show where that comes from. We're going to be looking at bending stress. We're looking at shear stress, some things to keep in mind. Oh, by the way, this is the testing apparatus that'll be recorded. Some things to keep in mind are these questions. Which joist withstood the greatest loading before rupture, before failure? You could see that from the data, right? From the test results, which joist displayed the best load to deflection ratio? Like I said, we'll be calculating ratios. If defects were present in each sample, what significance did the defects have on the test results? You'll see that in a little bit. And what advantage and disadvantage, what is the advantage and disadvantage of each type of joist? Now when you're answering those questions, you are only doing the solid and the TJI, the wood I-joist. You're not actually doing the glue lam. That's just for fun to see how much stronger it is. So as far as the video that we're going to watch, this is not a video that I recorded. This is the video from last semester that I am recycling. So we're going to see how this technology works out for us. It is on YouTube. I'll give you the direct link on YouTube as well, as if you want to watch it directly. Otherwise, what I'll be doing is watching it with you, stopping, narrating, and emphasizing pieces you might want to note. So let's go ahead and start it.
All right, we're going to start this test. This is our last lab for the semester. This is what we're going to...
It's not our last lab for the semester.
We're going to do our deflection on our 2x12s. We're going to use our dimensional lumber, 2x12s by 5 foot long. We're going to do I-joist, which will be the 11 7/8 with the 2 1/4 inch rim on them. And then for good measure, we'll do 2 of each of those, 2 of the 2x12 dimensional lumber, and then 2 of the I-joists. You're going to take your data, you're going to average the values for those, and then we're going to do 1 of the LVL with a micro lamp, okay? Just for good measure. You won't use that to answer the question. You'll only use the dimensional lumber and the I-joists. Okay? The LVL, just to show you how strong they are. We're not going to use that data for any of the questions or any of the calculations in the lab itself. All right, so I have a 2x12 loaded here. I did add right here, I did add a little bracket on there so that we can measure deflection, so that we can measure how much deflection we get as we put the load on there. I'll talk a little bit more as we get started. So I'm going to come back here, I'm going to actually adjust the head down, not up. Make sure none of my cables are in the road. I'm going to bring this down until it's almost touching. Not quite touching. We don't really want it to be touching. And I'm going to lock the clamp. What that does is lock the clamps right here. I don't know if that's showing up in the video. On these bars right here, it locks the head in place. And then now our our center cylinder, the cylinder right above here with our load cylinder, that's going to put our load on here. We have 48 inches between the two outside centers, 16 inches between the two centers here, which gives us a 32-inch span, or 16 inches for A, 1/2 the span length. Okay? So you're going to use 16 inches for A when you actually do the calculations. All right, so we're going to go ahead and zero the deflection out. We've got our close to zero. This other display is displayed on the concrete tester there. I have it hooked to this cable right here runs over our concrete tester, and that's going to give us the load cell on this particular device. Okay? So now I'm going to come over here, I'm going to hit start load. I'm going to start it. We should hear it kind of ramp up a little bit in a second as it starts to put a load on. And then we should see the load start to change. We should see the deflection start to change right there. And what you're going to do on the deflection, you're going to go like every 1,000 pounds when you watch the video.
All right, so instead of every 1,000, we're doing every 2,000. You'll hear him say that in just a little bit. But at every 2,000, what we're going to do is we're going to measure the deflection. So going back to your sheet and comparing it to the video, what I see is at about 2,082, I have a deflection of 0.0163. So this is the solid member. This is the first reading. That's what that 1 means. Deflection 0.0163. And a load at that time was 2,082. So you're going to continue to do that at every 2,000 pound increment. Sample 1 won't go real high, as you'll see a little bit, but sample 2 and the other ones will. And maybe I don't want to give it away, but there's a little knot right there. That's going to be the real difference there. So let's continue on with this video. And once again, now pause it every time it comes to 2,000 and get those readings. I will not be pausing it from this point forward.
And then we'll write down what the deflection was at 1,000, what that deflection was at 2,000, at 3,000, and so forth. Again, if you wanted to do it every 2,000 or 7,000, that's fine too. We just kind of want to get an idea, compare the two, from one to the other. Okay? This one here is going to be pretty low. I'm actually going to move this out of the way. And it continues to crack. Normally we leave that deflection in there until about 10,000 pounds, but this one here is a pretty weak one because of that knot and that imperfection right there. So right now it's forming right here at this knot. We're going to go a little further. Typically, in most cases, we'll see that most of the damage will occur up here in compression first, but final failure won't occur until the tension is built on the bottom. Slightest amount of rebound, but not enough to really consider that to be rebound. Okay? I'm going to go ahead and raise, so I'm going to unlock the clamp. I'm going to raise this stuff out of the way. Both of these out of our cables are where they're going to get pitched. Sure. Now I'm going to go ahead and take the bracket off here. Try not to knock the cameras in there out of the way. Or lose the screw. Okay. So, take this one out. I'm going to grab another one. I'm going to try to grab a little bit better one.
All right, I'm going to pause it and fast forward till he loads in the other one. Nothing too exciting here.
A little bit. Get it back where I want it. We'll reset our other one. Again, that last one that had a peak of 5,403.
So that 5,403 you should be recording in your sheet as well. That would go under sample 1 peak value. What was it, 5,403, I believe, something like that, right? So that's where that would go. Back to the video for sample number 2.
Next, we'll go ahead and start another test tube. Okay, so now we've got our deflection set. Now we'll run our head back down. Okay, lock the clamp. And reset our deflection. Rotate that towards the camera since I moved the camera. I'm going to go ahead and hit start. Okay. I would expect that this one will probably go over 10,000. Maybe up to 12 or 14,000. We'll see. It's just a much clearer piece of lumber. I know there's a little bit of error on the meter over there. That negative 247, not going to make a lot.
Okay, as a reminder, you should be taking measurements every 2,000. So we just passed the 2,000 mark, right?
A difference when we're getting up into the 10,000s. Again, make sure that when you watch the video, you kind of stop it and look at that deflection for every 2,000 or so and write down that number so that we can compare the deflection of the different samples. When we get to over 10,000, I'm going to go ahead and move this out of the way. Just if it snaps and breaks again, I don't want it damaging that instrument. In the past, our dimensional lumber anywhere from about 5,000 to about 18,000. Okay? Typical pieces are somewhere around 12 or 14. Okay? It's a good clear lumber. Yeah, this one you notice that we got a lot of damage right underneath one of the clamps or the compression, but we're not going to see failure until the tension along the bottom actually fails. Right? So this one I would say is actually pretty exceptional so far. We've got a little more compression on it at the top. Significant compression there. Hard to really see that with that camera. We're waiting for the tension to break on the bottom. Actually move this camera around as we're doing this because I kind of want to show you what we've got. So we can see here where we've got significant compression going on. Down here, we've got significant compression going on. Over here, we've got pretty good compression going on. And right down there, okay? So we've had a lot of compression on it. The rule is don't move the camera, it's just a pain to adjust. Alright, so let's see. Still moving, but we're starting, it's hard for you guys to see it, but this top piece is starting to twist. Alright? If it twists too much, then I gotta stop the test, because it will tend to mess up my fixture. Alright? We'll let it go a little bit longer, see what happens. As long as it doesn't continue to rotate around. Here we got a lower limit on stroke that showed up. So that's as far as it's going to go. So what we're going to do is we're going to stop and return it to 0.
All right, so if you didn't follow what happened, basically the machine ran out of room to push down on this. So what Brent's doing is he's going to reset the machine. I'll go ahead and fast forward so we don't need to watch that part. And then he's loading it back up.
First time we got 19,000. So we do the 19,000. Alright, unload this sample. We're going to do our eye joists.
So in case you didn't read that, 18,840 for the maximum. Once again, I'll fast forward till he gets that eye joist in there.
Alright, so we're going to use an eye joist. These are our eye joists. We can see that our particular eye joists are using a micro lamb for the top and bottom rail on them. Kind of do an in view hopefully in the camera here. Kind of see an in view of it. That micro lamb has this piece of OSB embedded partway in each side there for the rib. Okay? So OSB for our web and micro lambs for our two rails. Advantage of the micro lamb gives us a wider nailing surface, about 2 1/4 inches. We're typically a 2 by 12 is only going to be about 1.5 inches wide. This is 2 1/4. Gives us a little bit more to nail to. Okay, a little bit nice and thick here, something to nail to. All right, so we're going to add our fixture to get our deflection. Okay, before I do that, you can see that my eye joist is flapping around on here. So what we're going to do is we're going to add these plates in here. And we add these plates to the fixture, but we make sure they're short so that they don't interfere with the strength. All we're going to do is hold it parallel or perpendicular to the fixture. And these on both sides, just to try to keep it from twisting so we get a pretty good test. Okay, we're going to bring the head down, lock the clamp, move our stuff out of the way here, reset our deflection. Well, I guess I need to put it under there first. Put our deflection under there, reset it, okay, check our camera to see, that's not too bad, and we got our 261, so I'm going to skip out of here, carry that. So I got that 261 there out of there, at least for now. Alright, so, alright, got everything set up, so we'll come over here, we're going to hit start, and hopefully we'll see the deflection start to change, and we're going to see the pound load change. Again, you want to report the deflection, so every 2,000 or every 1,000, you have 2,000, you have a deflection of about 0.017. Okay? And just keep track of that so you can fill in your chart where you land. So we do it every 2,000, 4,000, 6,000, 8,000, 10,000 on the deflection. So we can kind of get an idea of how much load it holds for deflection. At about 10,000, I'm going to move this out of the way. And now I don't have to worry about deflection. I'm just going to worry about load. Now, typically our TGIs won't hold as much load as a twin piece of lumber. But they're going to hold more load than our typical knotted pieces or really crappy pieces of dimensional lumber. So they're usually much more consistent. Pretty much failed now. We're going to go ahead and release the load and have to return to 0 and then watch the rebound. You can see it rebounded quite a bit compared to our dimensional lumber. Again, our micro lambs, and we'll see that especially on the LVLs, will give a lot of rebound when we will release the load. Okay? Alright, so that was our first micro lamb. Let me go over here and get our feet. So 13,762. That's the piece we're going to use for that one. And of course our tear scale, when we go from test to test, doesn't stay with us. Raise this up. We're going to take our plate off for our deflection. Slide these plates out of the road. That's for me. So pretty much broke. If you can see that in the camera right there, pretty much broke right through there. We're doing 2 of these. average them just like you're going to average those two pieces of dimensional lumber. One of those dimensional lumber was really low at the beginning, and one was really high. So that's typical with dimensional lumber. You get a lot of variation. We're going to find our engineered wood product like this high joist. They're going to be fairly consistent. Off the clamp. We're going to add our deflection plate. High tech. Worn out screwdriver bit. Alright, we're going to reset that deflection, check our camera to see if I bumped it. I did bump it a little bit. That will go right like that. Okay. The deflection, we're not going to worry about that, minus 277. Again, we're going all the way up to 12,000, 13,000. That's not a very big percent error. We'll ignore that under the circumstances. Alright, we'll go ahead and start. You should hear it start to load up. Shaking, that is the vibration from that when it's breaking. Alright, we'll just stop it about there. Turn it back to 0. Again, you can see that the top and bottom rails being out of those micro lamps, we got quite a bit of rebound on them. We get a lot of separation right here where there is a seam. Okay? Actually have a seam right there. It's hard to show you that because of the way this is set up. Alright, so we're going to go ahead and run this up and we're going to do a micro lamp. Alright, let me go actually get the peak for this one. Back over here to this machine, see what we got for a peak. Alright, we got 11,929 for the peak. Again, that's probably about 279 below, because that's kind of our error for going out this our particular load cell. Joints, again, not quite as high, but pretty close. That 12, almost 12,000. The first one we got a little over 13. Those are pretty close to each other compared to the dimensional lumber. Again, it was this split right here, kind of failed right there where those two pieces of OSB came together. a micro lam. Again, you're not going to compare this to the other one as far as the question or the calculations. I'm going to kind of hold it up here. Hopefully that camera's giving you a good view. This has little 1/8 inch laminations, okay? The advantage of those laminations is any defect like that, a knot right there, is only 1 layer thick, okay? The layer behind it doesn't have a defect in that exact same spot. Same with these knots up here. Again, they're only going to be 1 layer thick. So the defect's only going to affect 1 layer at a time, okay? So go ahead and drop this in here. The other thing is this is all 2 inches by 11 7/8. We'll go ahead and do the deflection. Main difference on this one is I'm going to set the scale. I'm going to put it on 100%. This one should go up around 25, 30 thousandths, something like that. So we'll leave the deflection on there a little longer, but remember that we'll put a lot more load on this one than the other ones. Alright, bring it down, lock it in place. Again, depending on how much deflection we get on this, we may have to do it twice like we did that other one. Alright, so let me just check everything. 0 or deflection. Looks like their view's not too bad. I'll knock it up just a little bit. Over just slightly. Try to catch as much of it as we can. And I'm going to come inside here, put it on 100% for the load. That load. Should start. Should here start to load up. Again, we do have that 278 error for not being zeroed. Again, we could add that to our final number. This is an MTS 810 material testing system from the late 70s. Pretty old technology. The display unit actually doesn't work. That's why we're using the display unit on our concrete tester. You see, we're already at 20,000. Again, only less than 100 thousandths deflection with 20,000 pound load. 25,000, 27 extra down. And I'm going to go ahead and move this out of the way here. Start to get some initial crunching that you can kind of hear. Crack in there, so we dropped the load. It's still holding significant load, 28,000, 29,000 pounds. See, we've got a little bit of fire and tension down there. Not quite as bad in compression, just because it is a little harder than those laminates on our edge there. Let this drop to about half of its maximum, so that up around 32,000, 33,000. When it gets down to the 16,000 or so, we're going to release the load. Or until we run out of half of this load. Alright, so we're going to release the load now and see what happens. Good. Did it rebound quite a bit? It did rebound, not quite as much as that one-eye joist, but it rebounded quite a bit. We can definitely see some parts peeling off here. failure. But again, it held, let's go check what the peak was. Here, 34,453. We really add that 270 to that. That would actually be our number. So it helped quite a bit, okay, compared to our standard piece of dimensional lumber. Again, these are not used in the same place. Our dimensional lumber and our I-joisters are used interchangeably, but this micro-lamp would be used as the beam that supports those. Okay? What we use for the beam to support those others. All right, that's it for this lab. Hopefully the calculations are pretty self-explanatory. I gave you both the formulas form and I explained what all the letters mean for each formula as far as the numbers that go in there.
All right, so hopefully that made sense. By now you should be able to fill out all of your load and deflections. Divide load by deflection. You'll get another column you can fill out here. Of course, we don't have a peak because of the deflection device was removed before we got there. But fill that out for sample 1, sample 2 for the solid, sample 1, sample 2 for the TGI, and also for the LVL, we only had the one sample, right? Answering these questions, these should make sense. You know, you can just plug in values. 48P, what are you using for P? Well, P is going to be the average between like the peak load for sample 1 and peak load for sample 2. Add those two together, divide by 2. That's what you use for that P value. B and H, you can see we actually have values for our solid and our TGIs for the B's and for our H's. So you should be able to put in those values as well. If you are curious where this is coming from, you probably are just going to plug it in and not really think about it. But we have talked about this because we said that sigma is equal to MC over I for bending stress. Remember that? Well, the moment in this case, the maximum moment is 8 times P, and I could show you where that comes from, but I'm not going to spend any more time with that. The C value, remember that was the height divided by 2, the whole thing divided by moment of inertia. We said that was 1/12 BH cubed, right? Well, if you do some math and rearrange around, you end up with 48H over BH squared. Do the algebra, check it out for yourself. So we know where this is coming from, but you can just plug it in at this point. And give me the modulus of rupture, which is the same thing as the maximum bending stress. I probably should change the wording. Maximum bending stress for the solid, maximum bending stress for TGI. Same thing with the shear, 3P, 4 times BH. The B times the H are already multiplied together for you, which you could do as well since you know B and H. And then find the shear stress, answer the questions, turn it in. Let me know if you have any questions or comments. And I will talk to you all next time. Thanks.